Welcome today. We will finally tackle one of the most fundamental problems for manipulators, namely the ability of describing the direct kinematics of the manipulator arm. We have already mentioned what we mean by that, namely the possibility of computing the pose, so the position and orientation of the end effector of the tool of the manipulator as a function of some joint variable which characterize the configuration of the arm. This is the classical way of interpreting the concept of direct kinematics. I will try also to extend it a little bit, namely including in this context also the idea of task kinematics, out of which the direct kinematics in the traditional sense is one particular, although very important example. But the concept can be generalized, and this concept is very useful for handling a variety of tasks that has to be performed by the end effector or by the robot as such in the real world. Okay, so direct kinematics. What is this concept? So we will study the geometric aspect of robot motion and the timing aspect of robot motion. And we already start doing this distinction. Geometry means no time, no motion, in fact, but a description of different posture of the robot arm depending on joint variables. And timing's aspect means we add to this the fact that time is passing by, so we will be interested later on in differential kinematics, which describes relationship between velocities or acceleration and so on. Okay? The point here is no matter if it's still or moving, we just want to describe this motion, both in its geometric and timing components, without looking at the causes that will produce this motion. Okay? So it's kind of an analysis of what's going on. And for most of the time, we will assume that we can command some velocity while we are not really commanding velocity with our actuators. We are commanding torques at the output of our actuators, and these torques will accelerate the motion depending on inertia, distribution of masses, gravity, other disturbances, and so on. But this is the subject of another more complex topic, which is dynamic of robot manipulator. So in dynamics, you look for causes producing motion or exchanged forces with the environment. In kinematics, you're only looking at motion per se, no matter which are the causes. Okay, so you may understand that kinematics is part of the dynamics because you have first to describe motion, then you relate this motion with the causes that produce motion. Okay? So this will be our study now. And for most of the time, I would say for all this Robotics 1 course, we will look at a robot as a kinematic chain of rigid bodies. Most of the time as an open kinematic chain, so without loops in the structure, so that we can identify the sequence of bodies in motion from the base to the end effector. There is no ambiguity in saying what comes first, which happens when you have a kinematic loop. Okay? And this rigid body will be connected by joints, and we will consider only two types of joints. There are multiple types in general, but these are the elementary one, and you can decompose other more complex connection between successive links with a revolute or prismatic joint. So what are the motivations for doing this? Well, this is central to whatever one would like to describe concerning a robot manipulator, but here are a few items. First of all, functional aspects. So you have a robot, you want to know where to place the robot within let's say an industrial cell, in such a way that its end effector can reach objects and parts needed for performing production. So you need to know the workspace of operation. And this requires the knowledge of the direct kinematics of the arm. Okay? Also, if you want to improve accuracy, remember the discussion that we had about measurement systems, you need to calibrate the kinematics, and for calibrating some kinematic model, you need the nominal model first, and then you can perform additional experiment to do calibration. We will see that calibration as a subject as one of the first topics at the beginning of next semester in Robotics 2. And then there are operational aspects which are fundamental. This loop here between these two things is central to all the topic. So let's start with this. Where to define a task for a robot? Actually, we can define a task even without the robot. We have things to be assembled. So they are on a table, for instance. And then we know that first we have to take part A, then bring it in contact with part B, then take a part C and put it together so that it becomes a single part, then rotate this part and insert in another hole, and so on and so on. There's no robot there. So the task description and definition and description is made in the Cartesian space. Okay? Now you put a robot there, and you want to execute this elementary motion. You don't have a flying robot that goes everywhere and can take parts and reorient it and put it in a different place, although one can think about drones doing this, but this is another story, especially if you have heavy loads. So you need to actuate this task, to realize this task. So you have the robot, and the actuator for a robot are not in the Cartesian space. They are placed along the structure. And in particular, they will move the joints. So we have two spaces. One where we define the task, the Cartesian space, and one where we execute the task, which is the joint space. Now, if we give command in the joint space, then this will have an effect on, for the time being, position and orientation of the end effector, so that we can evaluate also the performance in doing the task, if we are doing well or not. If the task is go along this line, we give some motion in the joint space of the arm, the end effector will move accordingly, but it may not go exactly along the line, so we evaluate the performance again in the task space. Okay? So you see, it's a back and forth operation. Actually, this is a simplification, because in principle you could have also a third space, so I'm just expanding this. You may have an actuator space. This will go into a joint space, and this will go into a task space or Cartesian. So I have had the third space here, which in that slide is practically merged together. Sorry. So again, you define the task here. In order to realize, you would like to have some geometric or timed motion of the joints. In order to realize this, you have to command the actuators in a proper way. Now, if the actuators, you have one motor per joint placed exactly at the joint, let's say a DC motor doing some rotation, then scaled by a transmission ratio, but then moving exactly that joint, so the actuator space and the joint space can be merged together. It's just a scaling factor, maybe. But you may have different situations where two joints, for instance, my shoulder and my elbow, are moved by two motors which are on the basis of the structure. And they cooperate together. Both motors are moving both joints, not separately. So you have some mixing of things, and then it's worth to distinguish between the actuator space, so the rotation of the single motors on the motor axis, and the rotation of the two joints which are connected through complex transmission to this. But if you assume that you have one motor per joint placed on the joint axis or somewhere else, but through transmission you have at the end only a factor of scaling, then you can merge actuator space and joint space. So you see that even in this more complex case, you define a task here, you want to move in the joint space. In order to do this, you move the motors properly. When you move the motor, the joints will move, and the end effector will move, and then you check the performance. Okay? So it's a generalization of this. And in these different spaces, and these passages between spaces is at the core of our analysis, and also of our synthesis. So we will use a concept of planning trajectories, and we can plan trajectory. We should plan them in the Cartesian space, but sometimes it's useful or more easy to plan them in the joint space. We will program tasks, and again, we can decide where to program tasks directly in the task space or more easily, although more difficult to visualize in the joint space, and then do motion control. And by motion control is the natural way, as I'm presenting it, would be to close the error feedback loop at the task level, because there is where the task is defined, there is where I evaluate the actual performance, I compare them, and I see an error, and then I correct my command in feedback. Okay. Still, in some cases, I may transfer the task in the joint space, then measure the performance in the joint space, have an error in the joint space, and then react to this error in the joint space. Always giving command for the actuators, because everything boils down in giving corrected commands to the actuators. Okay? So, motion control, again, can be defined with this idea in mind. We will come back to this when we will talk about kinematic control, either with task error or with joint space errors, with respect to some planned trajectory. So we see that kinematics is important. Now let's try to be a bit more formal. So forget now about actuator space or merge this into the joint space. So we will have now, from now on, only two spaces. One, the space of the joints of the robot, and one, the space, Cartesian space for the end effector of the robot. Now we will, and here is the generalization, rather than speaking only about Cartesian space, although we can have this in the back of our minds so that we can visualize what we are thinking. So Cartesian space means, for instance, position and orientation of the end effector. But more in general, we may have a task space where the task is defined. And I give you immediately one example. For instance, your task space would be to move the end effector, which carries a camera, and in such a way that in the image plane of the camera, you will see some feature moving to certain desired places. So the task is defined in 3D. No, it's in the image plane of the camera. Okay? So can I relate the motion in this task space, so the motion of the feature on the image plane, to the motion of the joint? Certainly I can do it. And this will be the direct kinematic of this particular task. And the most common task is just moving the position and the orientation of the end effector. But you can imagine a variety of other tasks, not strictly remaining in the Cartesian space, and this is why it's useful to be a little bit more general. The basic joint to Cartesian space transformation, which is the classical kinematics, will always be needed anyway. But out of that, or combined with other information, you can build what we called the task kinematics for the task at hand, okay? And related to the specific robot. So with this in mind, we have a problem of parameterization. So the first choice that we have to do, so we have a space, how we describe where we are in this space. So we need a parameterization. Let's start with the joint space. We have mentioned that the joints of the robot will be typically of one of the two nature, either prismatic or revolute, and we need some variable for each of these joints. And since each joint gives 1 degree of freedom, if the robot has n joints, no matter which is the nature of these joints, we will need probably n variable, which are used to parameterize the joint space configuration of the robot. So we will have an array or a vector if you want. So here I prefer to use the term of array. So Q1 to Qn. And intuitively, this is pretty much simple. So I will have one variable for my shoulder, one variable for my elbow, 3 variables for my wrist, and so on and so on. Okay? Now, it's important. How do I choose this variable? I may need a systematic method, and we will use the so-called Denavit-Artenberg convention to define which kind of angle or linear quantities for prismatic joints we will use to parameterize the joint space. Okay? But in principle, you can use any set of n variable that you wish. And I'm making immediately an example, just to make sure that we are on the same mood. Suppose that you have a planar robot with 2 revolute joints. So this moves around this axis, and this moves around this axis. It's like the link 1 and 2 of a SCARA robot as seen from the top. Okay? Now I can use one variable for this joint and one variable for this joint. How do I define this variable? Well, if I look at this, I will say, okay, let's call this Q1, the angle with respect to some reference frame, the x0 axis of some reference frame, and let's use this angle, Q2, which is the angle of the second link with respect to the line. It's a pure geometric line. The robot will have some physical dimension, but we now take just the skeleton, the kinematic skeleton. We don't need more for describing kinematic, just skeletons, okay? So this angle will be the second variable. The robot has 2 degrees of freedom, 2 joints of the revolute type. I have defined 2 coordinates in the joint space. But why do I use this? Could I use, for instance, this angle? Let's call it Q2 prime. Would it be fine? Well, so there's a question. I can use it. This is the so-called absolute coordinate for such a structure, because both are defined with respect to a fixed axis, while the Q2 is a relative coordinate because it's defined with respect to the previous one. But both are feasible, provided that we choose a parameterization of the joint space, a 2-dimensional space, which is non-ambiguous. So that once I give you the number of this variable, you know exactly where the robot is. Okay? This means unambiguous. And minimal. I don't want to use more variable than strictly needed. If the robot has n degrees of freedom, by definition it has n degrees of freedom because n independent variables are sufficient to describe its configuration. So, enough, but not more than enough, this means. I make another simple example to understand what do I mean by that. So suppose that you have a pendulum that moves oscillates under an action of an actuator or just passively in the vertical plane. Now, it's 1 degree of freedom. This is clear to everybody, I hope. So which variable would you use to parameterize the joint space in this case? If I tell you that I want to know where this point is in the Cartesian space, what do I need to know?
One point in the join up to the wall.
1 point?
Where the robot is attached to the wall. Yeah.
This. So what do I describe from here? This point is fixed.
Yeah, but with this you can describe where is the end.
By knowing where is this point, I know where is the end. No. Because this point is fixed, this is moving. So if I give you this point, I don't know where is the end effector. Or maybe I understood, maybe you want to say something else. Maybe you want to say that, okay, as before, let's have here some x0, y0. So for instance, this angle here, this will be Q1. Okay? Or I could use this angle here. It's okay? Why not? No, just 1. Okay? But can I use, for instance, these two variables, x and y? So I'm using 2 coordinates for telling where this robot is, where the end effector is, in fact. It seems even better because I know directly where the end effector is. Is this good or bad? It's not meaning. It's unambiguous. It is unambiguous because I mean, for any configuration, I have 1 pair of x and y. Okay? But it's not minimal. And in fact, if I give you by chance a value of x and y, I may not even characterize the configuration, because if I give you an xy here, this does not correspond to any configuration of the robot because I'm not reaching that point. Unless I do some strange mapping, no, I will associate this configuration, the closest to this point. But I'm joking right now. And in fact, these 2 coordinates are not minimal, even because I know that they are not free to move arbitrarily. Because x squared plus y squared should always be the length of this link. Otherwise, this makes no sense. So in fact, I'm introducing 2 coordinates, and then I'm adding 1 constraint. So in fact, I need only 1 coordinate. It's exactly the same reasoning that we made for the minimal representation of orientation. Okay? So this means unambiguous and minimal. I think that now you have some more concrete examples. And this is for the joint space. Well, something similar should be made for the Cartesian or task space. So we have to choose a parameterization for what happened in this space. So we can introduce another array of m, different from n in general, variable R1 to Rm, with the same idea. So the task or the Cartesian space is described in an unambiguous way and in a minimal way by that set of variables. Okay? And this is the reason why we have introduced the minimal representation of orientation. Because now, for describing position and orientation of the end effector of the robot, we may use m equals 6, variable of the R1, R6 type. For instance, the first 3 may be x, y, z of the origin of a frame attached to the end effector of the robot. And R4, 5, 6 are 3 Euler angles, for instance, in any convention, z, y, z, which characterize the orientation of the frame attached to the end effector. So we'll have m equals 6 with 6 numbers and not matrices to carry over. This is the main reason for introducing minimal parameterization of orientation. Otherwise, it's very convenient to work with rotation matrices. Okay? So if we have m equals 6 here, then I assume that this n, well, what if I have a scalar robot? N is equal to what? For a scalar robot. N is scalar type. Huh? May change in size, but all scalar are made in the same way. N is equal to 4. Remember, 1, 2, 3, and 4. Okay? So I may have a kinematics which maps the 4 variable in the joint space of a scalar to the 6 variable of position and orientation of its end effector. Is suspect or it's fine? It's suspect. Why is suspect?
If there is one join, every join have 6 points in Cartesian space.
Let's put it that way. If I give you one configuration, so the 4 values of the joint angles or joint linear motion of a scalar robot, can I compute where is the position of its end effector and how the end effector is oriented?
I could, but...
Or I have too little information. This is what you're suggesting. I have 4 variables. Can I compute 6 variables out of these 4? Any others? Because otherwise he's the closest to me, so this is a natural attractor. But
the orientation is fixed, and I don't use 3 variables.
okay, but this can be set. No? This can be inside my mapping. I can discover that 2 out of these 6 variables are fixed. Okay, for instance. So you can do this in the forward path. So the number is not really important. What you cannot do is, if I give you arbitrary 6 number here, and I want to realize this number by placing the robot in a certain configuration with these 4 numbers, then it's not said that I can make it. Because I cannot cover a 6-dimensional space with a 4-dimensional one. It's just a matter of numbers. Okay? So in general, conclusion, any m and n can work, but we will most of the time use with n, which is larger or equal than m, so that we are guaranteed that we have enough degrees of freedom to place arbitrarily those variables through the direct kinematics. Sometimes m is, well, usually not larger than 6, but this is, again, not strictly necessary. And in the classical industrial case, we have m equals 6, position and orientation of the end effector, and n equals 6. So exactly the same number. And if we have a 7 degree of freedom robot, and our task is parameterized by m equals 6 variable, then we will have multiple solutions to the inverse problem. So I can realize this 6 variable with many combinations of my 7 variable. I have what is called kinematic redundancy, or better said, task redundancy, because now I'm thinking about a more general concept of specifying what I would like to do with my robot, not just position and orienting the end effector. Okay? So with this in mind, I think that everything is written on the slide. My direct kinematic mapping will be a function of the chosen generalized coordinate or parameterization of the joint space into the chosen values of parameterization of the Cartesian or task space. Okay, this is the direct kinematic, and no wonder this will be an easy problem. It has always one solution. Always. The difficult problem will be the inverse one. And in fact, we have reason about this concerning the example of the SCARA, where we said we have 6 variables desired for the task space, and we have 4 variables to find that solves this inverse function. And there is no inverse function well defined everywhere. And even where it's defined, even if we confine ourselves to orientation of the end effector of the SCARA, which are compatible with the mobility of the SCARA, so the end effector can always point in one direction, can never go there or there. So even if we define only 4 variables there, and we want to find the 4 here, this inverse function may have multiple solutions, or may have no solution at all if we are specifying a point which is out of the workspace. And sometimes it may have infinite solution. So the inverse kinematic problem is a tough problem. The direct one is easy, and we will do now the direct one. But in fact, we need to define the direct kinematics in order to have some equation to be solved in the inverse kinematic problem. Okay? I think I spent enough time on this slide. If you have questions, it's the right time to raise them. Okay, so open kinematics chain. So we will deal with something like this. This is one way of representing things. So I start from the base. I have the first joint with some variable. I will see how to define this. A second joint of the revolute type, the third joint prismatic, blah, blah, and so on. A number n. N may be 6, 7, 32. Okay, it's no bound on that. And then here I have an end effector with a reference frame. For instance, I use the 6 variable to describe the pose of this frame. The pose means position of its origin and orientation of the frame expressed in a minimal representation of orientation. Okay? Now we have, I think I have already, this is, here are a couple of more examples. For instance, if my task in the Cartesian space, but in a generic space, is I want to point with my end effector to a target, like a radar or a sun follower, okay? Just pointing. How many variables do I need? I need 2 variables for pointing in space. If I point on a plane, just on a plane, how many variables do I need to specify where I should point? Plane, just one angle. Okay. If I'm pointing in space, is rotation and then elevation, for instance. Okay. If I'm positioning an object, just positioning an object on the plane, how many parameters will I need to describe this task? Just 2. X and Y, yes, but also polar coordinate, R and theta, whatever. If I move to m equals 3, what I can find is, okay, with 3 variables of the R type are needed to specify the orientation in space. And we know that now, okay? Or if I want to position an object and orient it on a plane, vertical or horizontal or skewed, it's not important. Then I need 3 variables because I need 2 for positioning in the plane and 1 for orienting it in the plane. So 3, and so on and so on. I can give you an example with 7, which is 7, for instance, for our KUKA arm in the lab. We may specify the task as place the end effector somewhere, 3 variable of the R type. Orient the end effector as desired, other 3, and we are 6. And then place the elbow at a certain elevation. And this is possible no matter, once I have specified the pose of the end effector, I still have some degree of freedom. In fact, I have 7 joints. So I can specify that the elevation, just the y or the z coordinate of the elbow should be here or here or here, okay? So I have 7 variables for describing the r vector of my task. And you see that now it's not just something on the end effector. I have also used something which is along the chain. Still, I need to describe the whole chain, so I can then extract whatever I need from this description. Okay? Question on this? Now, we have talked about revolute and prismatic joints. Here is the standard classification that you find in any textbook concerning some symbols. We use an R for describing rotational degrees of freedom, or also called revolute joint, and a P for describing a translational joint, or also called prismatic. Okay? And here we see, just looking at the first 3 degrees of freedom, or joints of manipulators, we may have this type of classification. For instance, here we have seen the gantry type or Cartesian. They are prismatic, prismatic, prismatic. And typically these 3 joints are all orthogonal. One is like this, one is like this, and one goes like this. Or combination, first this, then this, then this. Or first this, then this, and then this, and so on. They are all possible combinations, that just permutation of the 3 Cartesian coordinates. Okay? But this is prismatic. The direct kinematic for this is very simple. Okay? And even the inverse kinematic is very simple. The more the revolute joint, the more difficult it is, because you're introducing trigonometric quantities, and then you have to invert trigonometric relationship. Essentially, this is the basic difficulty. Here we see a cylindric, or also called RPP, means that the first joint is revolute. Rotate. Then you have a prismatic going up and down, and a prismatic extending. So like cylindrical coordinates, in fact. Here you have a SCARA just for the first 3 joints. The SCARA has only one additional revolute joint at the end. But the first 3 are revolute, shoulder, revolute, elbow, and then prismatic up and down. So it's a RP. But even with this very simple example, you should start realizing that it's not enough to saying RRP or RPR or whatever. Because here, for instance, the 2 revolute joints are parallel. Okay? Here we have one prismatic joint going there and one prismatic joint going there, so they are orthogonal. And these are very special cases, because I can have a joint going there, a joint going there, just skewed in space. And I should be able to cover all these possible cases in one notation, one compact notation. And this is what Denavit and Hartenberg did many years ago. But let's continue this panoramic view. This is the so-called polar or spherical robot, 2 revolute joints and 1 prismatic. So again, rotation, elevation, and then extension. I cannot make it with my arm, as usual. This is called polar because these are the coordinates of this point. When I am expressing 2 angles and 1 distance, they are also called polar coordinate in 3D. It's also called spherical because if you look, if you freeze the last joint, so you freeze the last prismatic joint to a value, and use the other 2, the end effector of this robot moves on the surface of a sphere, and now if you move the 3rd joint, this sphere is growing or reducing. This is why the terminology is spherical. And finally, a fully articulated robot. This was called many years ago anthropomorphic because it's similar to the human arm, because it has only revolute joints. We don't have extension up to the hair. For the hair we have extension. But so this is RRR. Now we typically say articulated because we reserve anthropomorphic to really humanoid structure, not just to arm. But you can use also anthropomorphic if you're not too sensitive to these issues. Okay? So we have seen that we can classify the joints, but it's also important to look at how the axis of rotation or translation are placed in space with respect to each other. For instance, if I say just R, 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 I cannot say that this is the arm that I'm thinking of, because this could be also a robot like this. A fully planar structure with 3 axes which are all parallel. This is 3R, so R, but it has a different kinematics from that one, clearly enough. Okay? So we need more than just this. So, depending on what will be the task that we are describing, or even just the component of the Cartesian quantity that we want to include in our mapping, we have a function which characterizes the direct kinematic. And at the beginning, as usual, I will put a subscript here to remember that we have a robot. The robot is always the same, so it has their own cues in the joint space. But depending on what I want to describe in the Cartesian space or in a more general task space, I have a function which depends also on this. And so I call this function not just f, I will call it f of r because it's related to r. Then once I have familiarized with this concept, I will remove r because I know what I'm doing. Okay? Now, how do I compute this direct kinematic function from q to r? Well, by inspection. In easy cases, you don't need more. So with some geometry, some trigonometry. Well, if I move to the KUKA 7 degrees of freedom arm, I will be lost if I don't have a method. So we will see what is this method. There are some of them, but one is the more common and traditional, which goes through the following step. For each link, we assign a frame, because a link is a rigid body, and we assign a frame to the rigid body in a special way. And then we connect the position and orientation of this frame to the position of orientation of the frame at the following body. And we do this by a homogeneous transformation matrix, a 4x4 matrix. And then if we concatenate this from the base frame to the end effector frame, I have the direct kinematic as a product of homogeneous transformation matrix. And I could stop the lecture here, because now you can do whatever. But how can we assign frame in a useful way so that we don't introduce too many parameters? This is what we have to discuss from now on. But let's start with a simple example. So again, let's say the 2R case, so remove this and look at from top. By the way, in this description, that this plane of motion is vertical or horizontal makes no difference. Why? Because we are not looking at gravity moving, acting. We're just describing where it is and later on how it moves without looking at the causes. Okay, this is kinematics. So, again, I'm using Q1 and Q2, the first. I've canceled the blackboard, but I'm using the first two choices for angles. So Q1 with respect to some fixed reference axis x, and Q2, which is this incremental angle with respect to the prolongation of the first link. Again, these two variables work even if, and now I'm doing several examples on the blackboard today. Suppose that your robot is planar, but the first link is made like this, and the second link is made like this. Okay. Do I have a problem? No, because if I have, let's say, my x0 axis is here, and I've just rotated it for convenience. So I can take as Q1 this angle. Okay? So if this goes like a moon or like an S or is straight, it makes no difference at all from a kinematic point of view. Moves exactly in the same way. Sure, if I have obstacle in the workspace, it matters the geometric size and form of the link, but this is not our problem now. And again, here I can take the prolongation of this and then take this as Q2. So you see that for what it matters, this is like having this link and this link. And this will be, sorry, L1, and this will be L2. So if I sketch things in a skeleton way like this, I'm not losing any information at all. It's clear this. Okay, so Q1 and Q2, the two link lengths may be needed, but the link length in that sense, not in physical size, but in kinematic size. And this is enough for my joint space. Now, suppose that I want to describe something in the Cartesian space at the end effector level. And on purpose, I'm using m larger than n, and just to show you that we can do it. The direct computation goes without problem. So, for instance, I'm taking the coordinate of the origins of a frame attached to the gripper. So Px and Py are the two coordinates in the plane. And then some orientation of this frame, which moves with the arm, change direction with the arm. And I'm specifying only one angle I need for doing this in the plane. And this the angle phi with respect to one axis, let's say the same x-axis. Okay? So my r is given by Px, Py, and phi. And now I have to write r equal f of q. Well, this is easy. Just project things on the x-axis and on the y-axis. So here Px will be this segment, which is L1 cosine of q1, plus this segment, which is L2 cosine of q1 plus q2. You see the absolute angle. Similarly, for the y-coordinate, it's just change cosine with sines. So don't forget trigonometry. And finally, look at this. The orientation of the tip in the plane is just the sum of these two angles. In fact, it's the absolute orientation. And we have just said that the second link, if I'm describing in terms of absolute orientation, I should sum this angle plus this. And in fact, this is what I found here. Clear enough? So you see that I could put here other things. Maybe something will not be a function of q. For instance, if I want to specify the z coordinate, well, the z coordinate will be pz equals 0 or pz equals some constant because this plane. So it's not a function of q. Who cares? This means that I cannot change q and change this variable. But I can write whatever I need. And of course, then I need to see what kind of mobility do I get by moving the q's in terms of obtaining a motion for the r. Okay? This is the subject of discussion. So this is easy. Can we do this for other structure? Well, I would say if we confine ourselves to the planar case, there's no need of introducing the Navier-Tartenberg notation and so on. Because things can be carried on even if you have 7 revolute joints and links that moves in the plane. It's just an extension of this. You may have plus L3 cosine of Q1 plus Q2, Q3, and so on up to whatever n you want to use. Okay? But as soon as we move out of a plane, then we may run into trouble. So we need a systematic method for more general cases. And here we are. So we start we now take the assumption of open kinematic chain, and we start numbering bodies or links and joints from the base to the top, so to the end effector. And we can do this in a unique way. And pay attention, we start with the base of the robot. So the base is link 0. Pay attention. This is not moving if we considering fixed base manipulator. If the manipulator is mounted on a platform, so it becomes a mobile manipulator, then of course this frame will move with the platform. But relative to it, it's like seeing no motion. Okay, so we just decouple this problem of moving the base with some platform and from the base to the end effector, which is our fixed base manipulator. So for us, almost all the time, the base, or the so-called link 0, will be fixed in absolute terms. Then we have the first joint, revolute or prismatic. Here is revolute, so joint 1. Following joint 1, we have link 1. Then we will have joint 2. Following joint 2, we will have link 2, and so on and so on. So we have the 0 link or base, and then we have joint link with the same index. Up to the last one, joint n, which will move link n, which carries the gripper or whatever end effector you need. So you see that in our case, we have a chain of n plus 1 bodies, including the base. Only n of these bodies are moving from 1 to n. And these n plus 1 bodies are interconnected by n joints. And this is the typical notation that is used for a revolute joint, so a cylinder, so we can rotate around the joint axis. And this is a prismatic joint, so this kind of parallelepiped, and we can translate along this joint axis. But the joint axis is fundamental. You see that it's always one axis, and either we rotate around this axis or we translate around this axis. This is the joint axis, which covers both the revolute and the prismatic case. Okay. Now, it's early in the morning, so bear with me and have some spatial reasoning. Spatial reasoning. So imagine, I don't want to make a commercial, but imagine there are two joint axes in space. So this is joint I, and this is joint I plus 1. So it's the immediate following one. So these are two axes. And of course, these two axes are not fixed in space. They move together with the structure. Imagine this joint axis and this joint axis. Well, when I move my arm, this joint axis move one with respect to the other, and so on and so on. Okay, so how we characterize their relative position in space in a compact way? I don't know if you ever thought about this, but this is the principle of Denavit and Hartenberg notation. So the first thing that you can do, you take two, in general, skewed axes. You can find a unique common normal. So another axis, which is incident to joint I and joint I plus 1 at 90 degrees. Are you convinced that there's a unique one in general? There's only one. Huh? It's hard to visualize, but so this will be called. This is the common normal. It will be called axis of the link, the kinematic axis. This one, not this one. Okay. So it's the common normal between two successive joint axes. And since this is joint I and this is joint I plus 1, we know that in between there is link I. Remember, joint I, link I, joint I plus 1, link I plus 1. So this is somewhere here there is a link I. So this will be the axis of link I. Okay? Now, it is always defined, this common normal.
Because if I move the segment between A and B, I change the angle and I can put different situation.
If I change, okay, if I change this axis, this will change. Yeah, sure. But now, freeze the axis like this. Can I always define in a unique way, define in a unique way a common normal? So what are the special cases? For instance, if they are parallel, can I define a common normal? Yes. How many? Infinite to the which power? Infinite to the 1. So all these axes are candidate for being link axes. In fact, here, this is exactly the case. Two parallel axes. I have taken this on the blackboard, but I could take also another axis here. There's no sense of doing that, but in principle I can do it. Okay? So, parallel. What are other special cases? Orthogonal. Really orthogonal like this or like this? Are these orthogonal? Like this. Why orthogonal? Cannot be like this. Orthogonal is a special case. So maybe another is a very special case. The less special case is incident. Can I define a common normal? Two axes incident. Two axes define a plane. There's one point of intersection. The common normal is the normal to the plane at the point of intersection. The common normal is there. The distance of the two axes along the common normal is 0. In fact, they are intersecting. But, so parallel, in the parallel case, you have infinite possible common normal. But the distance is uniquely defined. Along any of this is always the same distance. So if I have skewed cases, I have unique common normal and the distance is defined. If I have parallel axis, I have infinite number of common normal, but the distance is uniquely defined. If I have incident axis, no matter if they are orthogonal or not, the common normal is unique and the distance is 0. What is left as a special case? Did I cover all possibilities? Think about joint 3 and joint 4 of a scara. What happened? Joint 3 is the vertical axis going up and down, and joint 4 is it's the rotation around the same axis. So it's not just parallel, they are coincident. Can I define a common normal? Yes. Why not? I mean, what is the definition of a common normal? I take an axis, and this should be normal to the first axis and normal to the second axis. So I take one axis, I take one normal. Since the second axis is coincident, this will be normal also to the other one. Okay? So yes, how many common normal are there when I have two axes coincident? Infinite, it's easy. Infinite to which power? No. Why? So I can take any of this, and there are one infinity, and then move up and down second infinity. Okay? What is the distance? 0, along any of this. So you see that although I have multiple definitions, I can always define a common normal, maybe more than one, but then the distance computed along this common normal is always uniquely defined, eventually 0, but okay? So this is what we need, and this is called, we will call this distance, since we are talking about passing from joint I to joint I plus 1 with link I, we will call this distance AI. It's the displacement from A to B if we have only one A and one B, so if this is the skewed case generic. Otherwise, whatever distance. It's always well defined, this displacement. Okay? Now, this is not enough to characterize these two axes in space, because I can have, imagine that I have these two axes like this. I have a common normal, but what if these axes are like this? It's not the same case. In fact, they may also be aligned, which is a special case. So there's still some angle missing in describing the relative position of these two joint axes in space. And this angle is characterized as follows. You take your common normal, or any common normal. You take a plane orthogonal to this normal. Pay attention, now it's orthogonal to the normal, like this. And then you project these two joint axes. Now you move them along the common normal. So they will intersect in this plane, and they will form an angle. For instance, if they were parallel, I can take any normal. I can take a plane at any place, and then I will move this, and on the plane they're doing alpha equals 0. Or, if now I'm giving also a direction to this axis, for instance, this one, they are still parallel, but when I bring them like this, they will make a pi angle in radians. Okay? So this angle is called twist angle, twist, between joint axes. For instance, here, the twist is 0 if we are taking this direction, or if we are taking both directions, or is pi if we are taking one going in and one going out as a twist angle. Okay? And typically in industrial robot, you find twist angle either 0 or 180 or plus or minus 90 degrees. There are some structures, there's a robot by Comau, which has at some point an alpha of 30 degrees. So you can have any values, but these are the most common one. And now the last conclusion here before moving to the next analogous slide is that, remember, now we have defined angle and distances. And if you have noticed, I've just changed this slide. Now you can find this slide on the web. These are the latest version. I uploaded them yesterday, tonight actually. I replaced distance by displacement, because distance is always a positive number. No? Distance cannot be negative, while displacement can carry a sign in one direction or the other. So remember that both these, we will see they carry a sign depending if we are going along some positive direction chosen for the frames or opposite. Or if we are moving counterclockwise around some axis, then the angle is positive, or clockwise, then the angle is negative. Okay? So remember, we have defined it like this, but once we put frames, we can also give sign to these quantities. So, and now we do the dual things, not for joint axis, but for link axis. So we have a joint axis I. What follows, the base of the robot is somewhere here. So we are moving, we are coming here, so link joint I following link I. And before joint I, we have link I minus 1. And before link I minus 1, we have joint I minus 1. And after link I, we have joint I plus 1. So, since we have pair of joint axes, for each pair we have a common normal, another common normal, and these common normals are what we have just defined, the axis of what? Of link I minus 1 and of link I. And now, on purpose, I made a generic strange structure like this, and I'm not showing the other joint, but you see that the joint axis, the link axis here of link I minus 1 may not live on the physical link itself. It's exactly like here. This is the link axis. All the body is there, so It's moving together with, it's attached to, but may not really physically be in place. Exactly in the same way that we said that we have an object, for instance, this object here, and we characterize this rigid object in space with a frame. So I can attach a frame, and then I say, where is the origin of this frame and how it is oriented, so I'm characterizing the pose of the object. But if this frame is here, provided that it is attached to the body, so it's moved exactly in the same way, then fine. So it needs not to be physically on the body that we are describing. Okay, and same thing here. So now we have two new axes, not of the joints, but of consecutive links. So axis of link I-1 and axis of link I. How are they positioned with respect to each other? We can specify this with other two numbers. Like before, we have introduced AI and alpha I, so some displacement, linear displacement, and some twist angle. And remember that those two variables, when we describe a kinematic chain, will always be constant. By the very nature of the fact that the robot has 1 degree of freedom joints. While here we'll define again one distance and one displacement and one angle, but this may vary with the configuration. So remember that here there are 2 points, C and D. We had A and B before. A and B in the previous slide where the common normal is intersecting the joint axis, I and I+1. Here is the same. C and D is where the link axes, which are common normal between joint axes. So this is common normal between this joint axis, which is not shown, and this joint axis I. And this is the common normal between this joint axis and joint axis not shown I+1. So they are common normal. This means that they intersect here at 90 degrees. There's no other way, otherwise they are not common normal. Okay, both intersect at 90 degrees. But typically not at the same position. So I have this displacement from C to D, which is the parameter DI. Okay, and now pay attention. If this joint is prismatic, what does it mean? That I can move along this joint axis. So if I froze everything else, what is from the base to here, so this is a unique rigid body, and now I'm moving this joint, which means that I translate along this axis. When I translate along this axis, this link which is before is not moving. This link which is after is translating. So this axis will remain fixed, and the point C is fixed, but this axis will move together with the link, up and down, so it will change the position of the point D. So this distance, or displacement, will be a variable if the joint is prismatic. Pay attention, if the joint is revolute, what are we doing is we are rotating around the joint axis. So this body will rotate around, and also this axis will rotate, but this point will not change. So this will be a constant. Okay, so depending on the fact that the joint is prismatic or revolute, this parameter will be constant or variable. Now, again, this is a displacement. We need an angle. And the angle is exactly in the dual fashion. You take, these are the axes of interest now. This is the common normal, because it's defined in. So we take a plane which is orthogonal to the common normal, and then we move this and project it on this plane, no matter which plane this is. And these two axes on the plane will make an angle, which is theta I. Okay? And this theta I, exactly for the dual reasoning to the previous case, is the angle between link axes. And if the joint is revolute, it will be a variable, because this is moving, no? It's rotating, so this is rotating, and its projection is rotating, so it's changing the angle theta, while di is constant. If it's prismatic, this is going up and down, so d is moving, but this axis is keeping the same direction, so its projection is not changing, so the angle theta is constant. Okay? So with respect to the previous the previous slide, we have still defined two variables, one linear and one angular. But in the previous case, both were constant, and now one of the two is constant and the other is variable, and this depends only on the nature of the joint. And as before, also these quantities will carry a sign, because if I'm rotating, now for instance the angle theta I, if it's variable, I have to now set some frame, so some direction, and if I see this rotation counterclockwise, theta I will be positive. If I see it clockwise, theta I will be negative. It's always theta I, remember what we comment on the blackboard a few lectures ago. So now once we have defined these four parameters, which are called de Navier-Hartenberg parameter, we just need to complete the story and attach to each link a frame and characterize position and orientation of one frame attached to link I-1 with respect to the frame attached to the following link I, using these four parameters. Just using these four parameters. Pay attention, if you take, no? No? Too delicate? Okay, I'm taking this. If you take two objects like this, fully free in space, and I'm telling you how many parameters do I need to characterize position and orientation of this with respect to this, what is the answer? So doing this is like doing position orientation of one frame. Well, I cannot do it without losing, and one frame here. Huh? So it's the relative position and orientation of two frames. If these are free to move arbitrarily, I need 6 parameters. Because this can be taken as the reference frame, and then I have an object which is moving in 3D and changing orientation. I need 6 parameters. While here, we will see that for going from one frame to the other, we need only 4. Why is that? Because these are not free to move arbitrarily, because they are connected through a joint, and this joint eliminates some degrees of freedom. I mean, it provides one motion, but in fact, avoids that you can move arbitrarily in other direction. Okay, and this is why we just need 4. So how are these frames placed? Pay attention, because this is the most common mistake, most difficult things to understand. But if you think that, so you have to place for link I-1, so I need to place a frame I-1, and I'm placing the Z I-1 axis, pay attention, along the joint axis I, not I-1. Okay? Then I will place the x-axis along the link axis of joint I-1, and y I am not even writing it, because it will complete a right-handed frame. And of course, I have chosen this direction, but I can arbitrarily choose the opposite one. It's good enough. I have chosen this direction, but I could have chosen this direction for x I-1, as long as it stays along the link axis. Okay? And similarly here, link I, frame I, Zi is along the joint axis I+1. Here it is. Again, up or down, it's not important. Xi is along the link axis of link I, and Yi is completing the orthogonal. Okay? This is the rule. It's simple. If you think about this, that frames goes with links, you won't make mistakes. So this is why I have added here these two comments. So reference frame I is attached to link I, moves together with. The fact that Zi is on joint I plus 1 should not be confusing. It's just a way of defining properly things. And then the other thing is that when you move joint I minus 1, you move link I minus 1, and so the frame I minus 1. Of course, you move also whatever is beyond, but just do incrementally. Okay? So with these two concepts, I hope that you won't get lost. And now, the procedure. The procedure is, okay, I have to define frame I. So here there are two frames shown, but now I'm talking about this. So frame I look at the joint axis I plus 1, and I put the Zi there. Up, going down. No, I can do whatever I wish. But once I have made a choice, then I keep this choice forever, okay? And I define accordingly my parameter. So Zi is along joint I plus 1. Then Xi is along the common normal between joint I and joint I plus 1, so along the link axis of link I. And if there are more common normals, I choose one of these. Okay? And again, I can choose this direction or the other. But these are the basic stuff. Why I is completed. Then, of course, these two axes will intersect. So the origins of frame I is placed exactly at the intersection of these two axes. Okay, because if I say that Xi is here and Zi is here, I'm still not saying where do they start. They start at the intersection point. And there is such an intersection point. And the origins will be there. And now we compute the 4 parameters. And these parameters should be interpreted as parameters for superposing this frame, pay attention, superposing this frame with elementary translation or rotation to this frame. You remember the interpretation of rotation matrices and then of homogeneous transformation matrices. They define the relative position and orientation of two frames, which means that through an homogeneous transformation matrix, I can bring one frame on top of the next one. And this is what I'm doing by elementary operation defined as translation or rotation around this axis. So the first one will be this, or maybe this parameter is defined as follows. AI is the length, quote unquote, of the link I axis. So it goes from D to this origin, and it's positive if I'm moving from D to OI along the chosen positive direction of XI. So in this case, AI will be a positive number. If I had chosen XI like this, I would have had the same absolute value of AI, but with a minus sign, because I'm going from D to OI, but moving in the opposite direction of the XI axis. Okay, pay attention to this. So this is constant. The next one is another distance, is from OI minus 1 to D. Again, this is variable if the joint I is prismatic, otherwise it's a constant. And in any case, it's positive if I'm moving from here to there in the same direction of the Zi minus 1 axis. So if I had chosen Zi minus 1 like this, and this was a revolute joint, so di was a constant, this constant would be di equal minus, let's say, 3 centimeter or 5 centimeter, minus 5 centimeter, okay? In this case, this is positive. And this is variable if the joint I is prismatic. Now the twist angle. Twist angle, remember, is the twist between joint axes. So now we have, due to the recursive nature of this assignment, I've started from frame 0 and I'm going to frame n, because I have link 0, link 1, link n, so I have n plus 1 frames. So I have already defined frame I minus 1. Now I'm defining how to get to frame I. So along the joint axis I and I plus 1, I have zi minus 1 and zi. So I need to compute this twist. But now I can give you a sign, because it's the angle between zi minus 1 and zi. If I bring it to a common plane and I look at the rotation, counterclockwise will be positive, clockwise will be negative. It's always alpha I. So here, more or less, if I take this z and I move it here, just moving along the common normal, I will go to this dashed line, and then I have to rotate around xi by this angle alpha I. Since I'm rotating counterclockwise, this alpha I for this picture would be, let's say, 20 degrees. Okay? It's clear enough? But this is again a constant. This will remain always like this. And finally, I have the angle between the x-axis. Remember, this is the twist between the joint axis, so between the z-axis, I minus 1 and I. This is the angle between the link axis, and on the link axis I have the x-axis of the frames. So between x minus 1 and xi, around the common normal, which is zi minus 1. So I take this direction, this is xi minus 1. I have to rotate, so to align with this one, and I'm rotating around z minus 1. So again, positive if theta I will be positive if this is counterclockwise, negative is clockwise. In this case is counterclockwise, so it's, in this case it's clockwise, yes, like ours. So this theta I in this configuration would be minus 15 degrees. Okay? And again, this will be variable if this is a revolute joint, because this frame and this link will rotate, and so this angle, aligning x minus 1 with xi, will change, so theta I will be the joint variable. See, out of these 4 parameters, ai and alpha I are always constant, and di and theta I, one is constant and the other is variable depending on the nature of joints. And let's make a break, but before making a break, I show this video, which is very popular on YouTube, because all students in robotics worldwide have problems the first time they see this Dynamit-Artenberg notation. So this is a very simple case, almost perfect. There is some change of notation, but I will note this, which assigned 2 frames on a structure which has 2 joints. But the structure is chosen complex enough to understand all the steps. But anyway, you will find it on the YouTube. So this is the first joint. Base frame or previous joint. So this is the rotation axis, and I put the z on the rotation axis. This is the first one, so I can choose x arbitrarily. Otherwise, it should be on the common normal. And why the green arrow is completed as a right-handed frame. Now the second joint is placed in this twisted way. It has its rotation axis. I put the z-axis there, and then I find the common normal. One is like this, one is like this. The common normal is the gray line shown there. And the x-axis, the new x-axis, is along the common normal. So I have defined a first Z blue axis, the second Z blue axis, and now the red arrow is belonging to the second frame. And the green missing axis is completed as a right-handed. Now let's look at this distance. This is the D, what we call the D displacement. From origin to the point of intersection of the common normal. Then the theta angle is the rotation between the x-axis around the common normal, which is the z-axis. Now this is called R, but in fact is what we have called A. This is the only difference. They call it R because this is like an axis of rotation, but A is the standard definition. And finally, the twist between the two axes. We have seen that one is horizontal, one is vertical, one is horizontal. And now there will be a twist of 90 degrees, but the sign is computed according to the fact that you are rotating. So this is a special case. They have changed the structure. Now the second joint has parallel axes with respect to the previous one. And now you have an infinite number of common normal, but the distance is always uniquely defined. This is theta. This is R, our A parameter, constant. And alpha is 0 because we are considering that they are pointing both in the same direction rather than one. And this is it. Okay? So you will see this at home. You have this in your package. And just note that the authors of this video use R in place of A, of our A, and do not use subscript. Pay attention, this makes a lot of difference. They have defined two frames without indices. So don't miss the fact that Zi minus 1 is a long joint axis I, and Zi is a long joint axis I plus 1, and frame I is attached to link I, and so on and so on. Okay? Let's make a break of about 15 minutes.